Welcome back. We will have our next speaker, Marcelo, telling us some exciting news about upper bound for multicolor Ramsey.
Thank you, Hong. Thank you for inviting me and organizing this wonderful workshop. So today I'm talking about this new upper bounds for multicolor Ramsey numbers. And this is all joint work with Paul Balister, Béla, Bollobás, Simon Griffiths, Eoin, Hurley, Rob Morris, Julian, Sahasrabudhe, and Marius Tiba. This large set of co-authors. And okay, so I'll get right into it. So the idea is that we are going to talk today about this quantity, which should be familiar for most people, which is the R-color Ramsey number, the R-color Kth Ramsey number. So it's the minimum n, such that for any R-coloring of the complete graph on n vertices, there is this a clique on a subgraph, monochromatic clique on k vertices. And this quantity goes back to Ramsey and Erdős and Szekeres. So Ramsey showed this is finite, and Erdős and Szekeres proved the first quantitative bound on this. And this is what we'll be interested in today's quantitative upper bounds of this quantity. So they show that RR of k is the most R to the RK. And it's still like a big open problem to determine what is the correct rate, both when k is constant and r is growing, and when r is constant and k is growing. So both cases are interesting. And we know some lower bounds. So first by Erdős, he used a random lower bound, and then there was like this blow up, like this, iterated construction by Abbott. And then this was improved further by Colin Ferber, Vigderson, Solling for lower bounds. But today I'll talk mainly about the upper bounds. And for R equals 2, there has been some extra improvement. So for over Erdős Szekeres result, so for Rodel did the first improvement over their result, and then Thomasson, Colin, and Sa, they showed that they showed a super polynomial improvement over the Erdős Szekeres result by the end, using these techniques of quasi-randomness. And last year we proved this result where we showed that an exponential improvement over this Erdős Szekeres bound but only for two colors. So we showed that there exists some positive delta such that the R2k is at most 4 minus delta to the k. And interestingly, this was improved quantitatively a lot by Gupta, Nijami, Noreen, and Wei this year, where they optimize use the same algorithm as us, but optimize everything very hard. And it is pretty exciting that they managed to get 3.8, because I thought it wouldn't go that far. So the best bounds are for two colors are now 3.8k, but there's some drawback of this method. And so here are the good things and the bad things about this method. So the one good thing is that the method works. Like it does improve the Szekeres bound for two colors, but it relies on this very, very delicate calculations that you have, like, it's very hard to check by hand. So in the paper we do something, okay, you can check by hand that it works, but it's very hard to see. Also, it's good that it works very well for off-diagonal case. So in the off-diagonal, you don't have to rely on very delicate calculations. It's much easier to see that things are going to work out. So this is good. So the proof was more designed for the off-diagonal case. While in the diagonal case, we had like this idea that we were trying for a long time to like a geometric type lemma to that should come into the proof, and in the end we couldn't like make it work. So we couldn't use this geometric lemma. Maybe this is good or bad depending on your taste. But yeah, I like the geometry, so maybe it's bad for me. And finally, it's good because it seems like this, for instance, from this recent paper, it seems like it gives like a decent improvement even over Erdős Szekeres, this 3.8. So that's that is quite interesting and unexpected to me. But the problem is that it doesn't do multicolor at all. Like it's the method that hits really a roadblock in doing the multicolor case, and it's because it relies on these very delicate calculations that just don't quite work for the multicolor. So today we're going to try to talk a bit about how to solve these things in the SAD column. And so this is the main goal of this new work. So the thing we show now is that for every number of colors R, there is this some delta such that we can get an exponential improvement over Erdős and Szekeres. And okay, so the exponential improvement gets worse as the number of colors gets bigger. So basically we can take delta to be, it is quite small. So like quantitatively, this is much worse than like for 2 colors, this gives much worse bounds than we had before. But it works for any number of colors. And I believe the proof is simpler as well. So this is the same list of co-authors plus Balister, Bollobás, Hurley, and Tiba. Okay, so the objective today is to tell you a bit about the proof of this result. Okay, so this idea that goes back to Thomason that we use is that, okay, if you want to try to improve the diagonal Ramsey numbers, it would be enough to find a large monochromatic book. And how large? Well, we call this the spine of the book. This is the spine. And these are the pages. And we would like to find a book with T vertices on the spine, and this many vertices at least as the pages. So basically, you can think that whenever you're doing the Erdős and Szekeres proof, upper bound for Ramsey numbers, you choose a vertex, and you look at its neighborhood. In its neighborhood, like we assume that all the colors are balanced, so its neighborhood takes 1 over R proportion of all the vertices. So every time you take a step in the Erdős and Szekeres proof, you're going down by a factor of 1 over R, which is the number of colors. So if we find a book with spine of size T, we would expect to go down by a factor of R to the minus T, but we can even afford a little bit of error, and the error is this e to the minus T squared over 4k. So if you imagine that T is like epsilon times K, the error will be like exponential of minus epsilon squared times K approximately. So this is the type of error that we can afford. And this will be crucial for us because our strategy now will be to show that we can find a book basically of this size at least. And this will give us this exponential improvement. Okay. And just before I talk about the book, there's like one more important thing to say, which is we assume in the beginning that all our coloring is balanced. And what do I mean by balanced is that, okay, the degree in color I of each vertex is going to be 1 over R plus little 1 times n. So it's basically, if there was a vertex such that its neighborhood has size bigger than n over R, then you could like do a step in the normal Erdős and Szekeres algorithm, and you will be winning over it because you are going down, instead of going down by a fraction of 1 over R, you're going down by something that is a little bit bigger than 1 over R. So we can assume that basically everyone has the same, has all the colors being the same size, and this assumption will be crucial for our next theorem. So the theorem here is that given a balanced coloring, meaning the thing I just said, like all the greens in all the colors are balanced, they are what they should be. For all epsilon and all t, there is a monochromatic book, TM book, with m being at least exponential of minus some constant depending on R, times epsilon squared times t, times R to the minus t times n. And notice that, okay, before we had like exponential of our error could have followed was exponential minus epsilon squared times k, but t is like epsilon times k. So it was actually our error before was epsilon, the error we can afford is epsilon times t, where here we have epsilon squared times t. So our error here is actually much smaller than the one we can afford. So this is very good for us. So it means that, okay, if you just take epsilon to be small enough, this quantity here, this constant r times epsilon squared, will surely be smaller than this epsilon here. And this is one of the reasons why our quantitative bounds are kind of bad, is because we take epsilon to be quite small, because we have this constant depending on r here. And this constant is like a polynomial in r. I should say like our bounds, they work for k being a polynomial in r, basically. Okay, it would be interesting to try to get out the same bounds, but with no dependence on r, because the dependence shouldn't be getting worse as r increases. Okay, and then we have this condition here that t needs to be smaller than epsilon log n, which kind of is saying that it's like saying that t is like epsilon times k. It's kind of what is it saying? By the way, let me know if there are any questions, for instance, about this statement or about anything I say in the talk. You can just ask. Okay. And so the main point is like to try now to find a large monochromatic book. And okay, so what is going to be the idea? The idea is, okay, so it's in this complicated picture here, but what is happening here? So the idea is the following. Normally, when you're doing the Erdős and Szekeres proof, you have some set X, which is your set of vertices, your world, and you take a vertex from the set, let's say U, and then you move this vertex either to the blue click or to the red click, so like to the red click or to the blue click, and you zoom into its neighborhood. But the problem is that you are zooming in on both colors. So like every time you do blue step, you also zoom in and you decrease the size of the red book as well. So the way we would like to fix this is by building one click in each color. So I'm just gonna say everything for two colors but it's the same, it generalizes. So now we're gonna build, instead of building the click for red, the book for red and the book for blue with the same vertex set here, we'll build two different books. So here's the book for red, is this T1 times T1 Y1, and this is the book for blue, is this T2 and Y2. And the idea is that now every time we do a blue step, only the blue book will shrink, but the red book won't shrink. And this is very important to us because it means that, okay, if every time you shrink the red book, you're shrinking by a factor of like approximately 1 over r, then this guy here, the size of y1, will basically should be like 1 over r to the size of t1, which is exactly what we want, times n. We won't be able to quite just shrink by a factor of 1 over r every time we zoom into y1, but we will be able to get close enough. So we got our little error, but basically that's what is happening. But there is a problem. Okay, if we want to shrink y1 every time by a factor of 1 over r, we need that the density, so actually the minimum degree between the vertices of x and the vertices of y1 doesn't shrink too much. And so we want to maintain the following quantity here, this pi, which is the minimum degree, so it's the minimum over x in x of the degree to yi over the size of yi. So we like this proportion here to always be bigger than 1 over r minus some function of epsilon. So every time we do a step, we need to take care of, okay, we automatically get the correct density, so like the yi shrinks by the correct amount, but we have to be careful to choose our set x prime here carefully inside our neighborhood in x, so that the density between these two sets is going to be maintained. So we maintain this property here, and this is the main is the tricky part of the proof, is to maintain this density across. And you and one interesting thing here about this is just, okay, if I do a red step and I zoom in here and zoom in here, notice that the minimum degree to y2 isn't altered, right? Like the minimum degree to y2 remains the same, so we don't need to worry about that. So we only need to worry when we are zooming on the right hand side as well. Okay, so I'll present to you now the algorithm that we use, and afterwards I'll prove that. I will just say a little bit for why this algorithm works. Okay, so at each step, either we are gonna do the following. We're gonna do something we call a red step. So we take the click T1 and we add this vertex U. And we're going to shrink the set X to some subset of the red neighborhood of U in X, right, of course. And we want to have the following property. We want the subset X prime isn't too small. And what do I mean by isn't too small? It can be actually seem quite small, like exponential of minus 1 over epsilon. Because, well, we're going to do in the end basically epsilon log n steps at most. So this is the amount of steps we can afford. And while y1 will be updated to just be the red neighborhood of U. And the goal is, okay, we would like to find an x prime here, subset of the red neighborhood, such that the density doesn't fall. And the density doesn't fall by this epsilon cubed over t. And okay, if we're doing t steps by the end, the density can fall by most epsilon cubed. Okay, but it's not clear that we can find this x prime. And in fact, we can't always find this x prime, even if we allow it to be quite small like this. But when we can't find it, we'll be able to show the following, that we can find another set X prime that doesn't need to be necessarily contained in the neighborhood of U, and with the property that it's going to be bigger than exponential of minus lambda times size of x, and lambda is very large, so it's larger than 1 over epsilon. So this set here can basically be very, very tiny, but that's going to be fine for us because whenever we zoom into the set by some by exponential of minus lambda, we are going to get a boost in density of this lambda squared over t. So if lambda is very large, basically we are getting a much larger boost in density. And in the end, these two things they balance out in the correct way. So and okay, I'm only talking about red here, but of course we are also building we can't guarantee that we always do this in red. Sometimes we do we either do one of these two things in red, or we do one of these two things in blue. So that's the whole algorithm. We can always guarantee that one of these 4 things will happen. So either we do this first step, red step, or we do the density boost step in red, or we do the blue step, or we do the density boost step in blue. Okay. So it's not clear. It shouldn't be clear now at all why this works. And okay, so the reason why it works, so there's this key lemma, and basically the reason why it works is that, okay, we can translate this thing into like a geometry problem, so something to do with inner products, because, okay, so it's not clear at all that you can translate into this problem. But the reason why you can't translate this is because basically what we are interested in is something that has to do with intersections of neighborhoods. So it's kind of natural that these intersections of neighborhoods can be translated into inner products if you do some mapping in the correct way. And the idea is to do like these R mappings, one map for each color, and each map is encoding like how much of a density boost we get if we do a step in a given color. So for instance, if this thing, the sigma I, sigma x, sigma y is like -1, it means that we are going to lose density in color I, and we're going to lose you normalize in the correct way so that it's the correct loss. And so what we want to, the main lemma we show is that if we have like these R mappings here from X to Rn, and the dimension doesn't matter at all, like you can like put any dimension here, then there exists some lambda greater or equal to 0, such that the following happen, and some color J, such that the probability over xy uniform in our vertex set that sigma x, sigma y, iy is greater or equal to -1, and sigma jx, sigma jy is greater than this lambda squared -1 is going to decay like this exponential in lambda. And okay, this dependence here, this e to the minus lambda versus this lambda squared, is exactly this dependence here. There's an e to the minus lambda here, and there's this lambda squared. And okay, and the point is that, it means that we can kind of find a set of pairs, large set of pairs that are correlated in every color. So their correlation isn't too bad in every color. So this is kind of saying like, okay, you have this pair xy, and for each pair xy with this property, it means that their common neighborhood in each color, so in all of the colors, is going to be decently correlated, and one of the colors it might be very correlated, or it might be not, like just normal, but we don't choose the lambda here. This lambda squared is just given to us by the proof. Okay, and maybe I'll just say very quickly something about this proof. So first, I just want to show that it's very easy to prove this lemma when r equals to 1. So the idea is just that, okay, this expectation here, you just look at the expectation of the inner product, it's positive. So it means that if you had an upper bound on this probability for all lambdas, you could integrate and you would show that the expectation is negative and get a contradiction. So it must mean that it's bigger than 1 over something, like 1 over 4 lambda squared, something integrable for some lambda. Okay. And okay, so I'm showing you this because the main idea is like a harder version of this, like a more involved version of this. So the idea is to take, like, for instance, for r equals 2, you take 2 variables, and now all the moments, we can show that all these moments are positive. And basically this means that if you compute any analytic function with all positive coefficients on these two, and take the expectation over this z1, z2, it's going to be positive. So we can take some function that has the same property as the linear function had for the r equals to 1 case. So basically it has to be negative in all the quadrants of the plane except for 1. And this is going to give us the proof. And yeah, basically now you do this integration, and you see that you get a contradiction because you have to have some mass in the positive quadrant. And the function we take is not quite this one, but this one is the simplest one I know that has this property. But we need like something that grows a little bit like slower than this one that grows exponentially. Okay, that's all I want to say for today.
Mm-hmm.